Netflix handles billions of video requests daily, and a significant portion of those involve shortened URLs shared across social media. That's a massive scale. Here's what most engineers get wrong. They don't realize how quickly the read volume explodes. In this video, we'll break down how to design a URL shortener that can handle millions of requests per second, covering everything from key generation to database sharding. Remember this, it comes back later when we discuss sharding strategies.
First, let's nail down the requirements. Functionally, we need to shorten a given URL and redirect to the original URL when the shortened URL is accessed. The system should support a REST API for shortening URLs. Non-functionally, the system must be highly available, have low latency for redirects, ideally under 100 milliseconds, and generate unique short URLs. We also need to consider the redirect type. Should we use a 301 permanent redirect or a 302 temporary redirect? For this design, we'll use 301 redirects for better caching by browsers and CDNs. The reason is that 301 redirects are cached indefinitely, reducing load on our servers. We also need to ensure the system is secure and prevent malicious users from creating shortened URLs that redirect to phishing sites.
Let's estimate our scale. Assuming 300 million URLs shortened per month, that's about 10 million per day. That's roughly 115 URLs per second. For storage, if each URL mapping takes 100 bytes, we need 1 gigabyte per day, or 365 gigabytes per year. For bandwidth, assuming 100 redirects per shortened URL per day, and each redirect is 1 kilobyte, that's 100 kilobytes per shortened URL per day. Multiply that by 10 million URLs, and we get 1 terabyte of bandwidth per day. This is where most people get wrong. They underestimate the bandwidth requirements. Remember this, it comes back later when we discuss CDN costs. We also need to consider the QPS for reads, which will be much higher than writes. If each shortened URL is accessed 100 times a day, that's 11,500 reads per second.
Now that we have a solid understanding of the requirements, let's dive into the high-level design. We'll have two main paths, one for shortening URLs, write, and one for redirecting, read. The write path involves receiving the long URL, generating a unique short key, and storing the mapping in a database. The read path involves receiving the short URL, retrieving the corresponding long URL from the database, and redirecting the user. We'll use a load balancer to distribute traffic, an API gateway to handle requests, and a cache to improve read performance. For the database, we'll use a NoSQL database like Cassandra because of its high write throughput and scalability. A relational database like Postgres would likely bottleneck under high write volume. We'll expose a REST API, post/API/v1/URLs, long URL, custom alias / expiry / to short URL, created at /. We use an API gateway because it allows us to add features like rate limiting and authentication in a centralized location. Alternatives like Nginx can be used as a reverse proxy, but an API gateway provides more features out of the box.
Let's dive deeper into the core logic. The key generation algorithm is crucial. We can use a sequential ID generator or a random ID generator. A sequential ID generator is simpler but can be predictable. A random ID generator provides better security but requires collision resolution. We'll use a random ID generator with base 62 encoding. Why base 62? Because it uses alphanumeric characters, A to Z, 0 to 9, allowing us to represent more values with fewer characters compared to base 10. The algorithm converts a numeric ID to a base 62 string. What happens if we get a collision? We can retry with a new random ID. To further reduce collisions, we can use Bloom filters to check if a generated short URL already exists before writing to the database. Most candidates stop here, but a strong answer also addresses concurrency. We must ensure that our ID generation is thread-safe to avoid duplicate IDs. Your interviewer will push back here. Why not use UUIDs instead? The answer is that UUIDs are 128-bit, resulting in longer short URLs. Base 62 allows us to represent the same number of URLs with fewer characters. We can use a library like Hashids for base 62 encoding, which provides a simple API for converting integers to short, unique strings. Another approach for ID generation is using Snowflake, which generates distributed unique IDs. However, Snowflake requires more infrastructure and is overkill for this use case.
Now, let's design the data model. We'll use a NoSQL database, like Cassandra. The schema will include the short URL, the original URL, a creation timestamp, and an optional expiration timestamp. The key will be the short URL, allowing for fast lookups. Pause here and think, what's missing from this schema? We also need to include audit fields like created at and updated at for tracking changes. We'll also add a user ID if we later decide to add user accounts. We chose Cassandra over a relational database because it offers better write scalability, but the trade-off is eventual consistency. This means reads might be stale for a short period. We also need to consider adding an index on the created at field for reporting purposes. Let's talk about scaling. Remember those billions of Netflix video requests we mentioned in the beginning? To handle that volume, we need caching, sharding, and rate limiting. We'll use a cache-aside pattern with Redis to cache the most frequently accessed URLs. This reduces database load and improves latency. For sharding, we can use consistent hashing based on the short URL. This distributes the data evenly across multiple database servers. We might be tempted to shard based on user ID, but that would create hotspots for popular users. For rate limiting, we can use a token bucket algorithm to prevent abuse. We can also use a CDN to cache the redirects at the edge, further reducing latency. The CDN also helps protect against DDoS attacks. An experienced interviewer will probe what happens at 10x scale. Here's the key. We'd need to reevaluate our sharding strategy and potentially add more cache layers. Consistent hashing ensures that when we add more servers, only a small percentage of keys need to be remapped. Remember the 1 terabyte of bandwidth we estimated? A CDN helps us handle that scale by caching content closer to the users.
Now let's consider reliability. We need to ensure fault tolerance, monitoring, and alerting. For fault tolerance, we'll use database replication and load balancing. If a database server fails, the load balancer will automatically redirect traffic to a healthy server. For monitoring, we'll track key metrics like request latency, error rate, and database load. For alerting, we'll set up thresholds for these metrics and trigger alerts when they are exceeded. This allows us to proactively identify and address issues before they impact users. We use Prometheus for monitoring because it's a pull-based system that scales well. Alternatives like push-based systems can be overwhelmed by high traffic. We'll also use Grafana to visualize the metrics.
In summary, we designed a highly scalable and reliable URL shortener. The key trade-offs were between consistency and availability, and between security and simplicity. The main bottleneck is likely the database, so we need to carefully monitor its performance and scale it as needed. Next steps would be to implement the design and conduct thorough testing. Remember, system design is all about making informed trade-offs and understanding the limitations of your choices.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.